Hi there, welcome to M Squared, a channel where we're going to take a deep dive into the history of science and uncover some of the lesser-known contributors to the field. Marietta Blau was a particle physicist who was born to a Jewish family in Vienna, Austria in 1894. In the early 1900s, Austrian schools were actually quite welcoming to women and girls. Marietta got her high school education and eventually got into the University of Vienna in 1914 studying science. 5 years later, Marietta was awarded her PhD with the thesis, A Study of the Absorption of Divergent Gamma Radiation. As a fresh postgrad, she spent some time at a German X-ray manufacturer doing R&D. She then took up a position at the university in Frankfurt am Main, teaching medical students radiology and publishing papers on photographic emulsion techniques with visible and X-radiation. After a few years, she returned to Austria to care for her mother. Luckily for her, though, Austria is one of the leading places in the world at the time for radioactivity research. The roots ran deep, with local mines supplying the raw materials and radiation sources that she needed. The Radium Institute was founded in 1910 in Vienna, and the director was actually an advocate for women, and he encouraged recent graduates of any gender to apply. Marietta landed a job there, one of a relatively high number of women at a research institute of its kind. Her earlier work with medical students gave her the background she needed to hone her process, making huge leaps forward in particle detection and publishing 6 papers in as many years. She experimented with different silver emulsions, fiddling with every variable to get the best resolution, the highest sensitivity to radiation, as well as a long shelf life to keep records of her experiments. She used different radiation sources to test her plates, including protons, alpha radiation or alpha particles, helium atoms with no electrons, beta radiation or electrons and positrons, and light, including gamma radiation, which is super high energy photons. The silver atoms in the emulsions decayed into smaller particles after they get hit by high-energy radiation, and they leave trails behind. Before her photographic plates, the only way that particle physicists could study these things were in cloud chambers, and they were, by nature, ephemeral. And though you could aim a camera at one of them, the cameras at the time could not capture the fine detail. You had to get the timing right, and the resolution just wasn't there, so no chance. Marietta's plates had the decay happen right on the plate, so you can't really get much higher resolution than that. Working with one of her students at the time, Herta Wambacher, they made one of the big breakthroughs of the day, capturing traces of the newly discovered neutron particle, the first to detect neutrons through these emulsion techniques. Their work was awarded the Ignaz L. Lebenspreis, a prestigious award given by the Austrian Academy of Sciences. Another cutting-edge discovery at the time were mysterious sources coming from the sky. There was mounting evidence from weather balloons that there was high-energy radiation in the upper atmosphere. But no one really knew what they were or where they were coming from. Was it some sort of process in the atmosphere, or were they actually coming from space? To find out, in 1937, Herta and Marietta took a trip up to Hafleckar, a mountain near Innsbruck in the Austrian Alps. At the research hut there, they left out some of their glass plates to be exposed to the cosmic radiation. They left the experiment running for 5 months. If the rays were indeed coming from space, the 2,300-metre elevation would give better results due to there being less atmosphere getting in the way. Upon returning, they found tracks on their plates, disintegration stars, evidence of the heavy particles in the emulsion being smashed by high-energy radiation. With some calculations, you can actually reverse engineer and work out the energy of the incoming radiation. You just have to add up all of the decay products and the bits and pieces and work out what was left over. This is the same principle that CERN uses and other particle accelerators. It all basically just comes down to the conservation of mass and the conservation of energy, which are equivalent using Einstein's E equals mc squared. Marietta and Herta published their results in Nature in 1937, and their work caused a buzz in the physics world. Heisenberg was one of their biggest fans. Marietta quickly designed some additional experiments to refine the results, and she published in Nature again the next year in 1938. Despite being a full-time researcher and scientist with several doctoral students, she didn't actually have a full-time paid position at the Radium Institute. It was only taking on consulting jobs, secondments, and grants that she was actually able to, make any money during her time working there. As precarious as this was, worse things were to come. Many of the scientists at the Radium Institute had actually joined up the Nazi Party during the 30s, and her own student Herta Wambacher was a card-carrying member. Though Marietta had worked with the Institute for years, in 1938 the situation became totally untenable. Some of her ex-colleagues started to scrub her name off her research, off her papers, and discredited her work in favour of Herta, even though it was Marietta who painstakingly worked out the optimal formulation for the silver emulsions, which was fundamental to all of the work that they did. And she was the supervisor. She had supporters like Hans Petersen, who at least insisted that their papers be published in Marietta's name first, because that's the alphabetical order at least. Eventually she fled Austria altogether the night before the annexation by the Nazis. Ellen Gleditsch, a friend from the University of Oslo, invited her up for a semester, and on the way she gave a guest lecture at the Niels Bohr Institute in Denmark. While she landed safely outside of the grip of the Nazi Party, with extremely lucky timing, basically all of her Jewish ex-colleagues were forced out of the institute. The erasure of her contributions only got worse. Herta was continuing to publish stuff based on their work together and not even crediting Marietta as a contributor, let alone an author, a co-author. After leaving Norway, she took up a job at the Technical University of Mexico City, a position that was organized for her by Einstein from his own exile in the US. Her network of friends back in Europe organized to send her experimental materials and bits and pieces over to her in Mexico rather than the Radium Institute, but it didn't really matter. All of her time was taken up teaching and taking soil samples, studying soil samples. After 3 years, she grew tired of the demanding teaching role and once again called on Einstein for help, who made a submission to the Mexican ambassador to the US on her behalf. I am taking the liberty of drawing your attention to a case close to my heart. Since 3 years, my colleague, the physicist Dr. Marietta Blau, lives in Mexico City. I know Miss Blau is a very capable experimental physicist who could render valuable service to your country. She is an experimental investigator in the field of radioactivity and cosmic rays. In 1944, she moved to New York and took up a job at the Canadian Radium and Uranium Corporation. Apparently, they've got a facility in New York. And finally, after years, she was able to get back into her research. She re-entered particle physics in a whole new paradigm. Atom smashers, particle accelerators were the big new thing. And she had a little catching up to do, but she was all right. Emulsion techniques were actually still in really high demand. I mean, there's a whole new particle zoo to identify and catalogue. She worked at Columbia, Brookhaven, and the University of Miami, and her reputation preceded her wherever she went as the Pope of emulsions in physics. But by 1960, her years of working with radiation had caught up with her. She was losing her vision to cataracts, and her health in general was just waning. She retired and returned to Vienna for financial reasons, once again being uprooted and exiled from her colleagues and friends. She actually returned to the Radium Institute, working with images from CERN, giving lectures and teaching some of the graduate students there. She won several awards during this time, but the whole thing was kind of bittersweet. The Austrian government didn't have any compensation available for refugees, and the only income she actually earned at this time were $200 monthly payments from US social services. She stopped working at the Radium Institute in 1964, and 6 years later in 1970 she succumbed to lung cancer and died. Despite her contributions to particle physics and physics in general, no journals published an obituary for her at the time. In 1950, the Nobel Prize for Physics was awarded to Cecil F. Powell for his work with silver emulsions on photographic plates. He performed his first experiment in 1938, and over the next 10 years discovered the pi meson particle. However, not only was Cecil not the first author on this paper that won him the award, the Nobel Prize Committee choosing to award it to him over the Brazilian first author, Lattes, he wasn't even the first person to conduct the experiment at all. Marietta and Herta had done their research. They had done that experiment and published the year before in 1937. I mean, Marietta's work was actually instrumental for how Powell conducted his experiments too. The Nobel Prize actually has rules in its bylaws to say that the winner of a prize must be the first person to make the discovery or invent the technology. So the devastating derailment of her career cannot be overstated. She was a pioneer in a fledgling field with a career all but cut short less than a year after publishing one of the most groundbreaking papers of its time. One of her biggest fans was Erwin Schrödinger, who nominated her for a Nobel Prize twice. And she was nominated a third time as well. One of those times was actually in 1950, the year that Cecil won instead. Thankfully, these days, there is an increasing interest in the stories of underrepresented, disadvantaged, and discriminated against people and their contributions to the scientific endeavour. So stories like hers are coming back into the light. And there's some really good papers that I read researching this video, and I've left them in the description. Thanks for watching. I'd love to hear from you in the comments if you've got any feedback or suggestions for future videos, and don't forget to like and subscribe.